to some extent because the modes that we're using are not the true modes. We know that the frequencies were substantial. To further emphasize how we got the same answer as previously, I'll give you a frequency response plot. Here's our tip displacement, and the two figures lie directly on top of each other for the direct and the modal solution. And we're not surprised by that. Now I'll just end with a couple comments about the method. Our frequencies had been calculated earlier by the Givens method, and we repeated that as a part of our current modal response process, and so the frequencies were correct to all significant figures, but as I mentioned previously, have the same modeling error baked into them due to only two elements as the previous direct run had. So we got exact comparison of two approximate methods. The MSc Nastran program uses an uncoupled solution algorithm. So when you do use these modes, then it's able to break that down into the sequential solution of a set of ordinary differential equations, in this case even algebraic equations, where the inversion of the complex mechanical impedance is used. So rather than a simultaneous solution, you do a sequential or an uncoupled solution of equations one at a time. Finally, we won't do a modal transient response. We haven't had the transient integration explained to us yet in this series. You'll get that in a few lectures. So we do need those ideas. This method also leads to uncoupled transient equations rather than the uncoupled, really algebraic equations that you do solve for the frequency response problem. I like to give small numerical examples that can be worked out by hand to illustrate these more exotic computer-based solutions. So for the modal response problem, I'm going to give a small problem based on our Lab 6 geometry. The problem's complicated enough that it takes two figures to state what the problem is. On this first figure, I will illustrate that we have this beam, which I'll tell you is basically the beam that we've looked at before. There's a force which has a vertical component both at the tip and the mid node, and in opposite sign sense. So when this one is up, this one's down. That will tend to excite a little shorter wavelength behavior in the structure. The structure will oscillate between these two extreme envelopes, where this is a cantilever beam clamped at the left end. Now the frequency is given as 180 here, and you know that that is I cap omega t. So we have that cap omega is 180, and that dimensionally is in radians per second. So you can figure the frequency out from that. To complete the physical description, I need to either give the physical characteristics of the beam or give them in generalized form. Here I give the generalized mass and the generalized stiffness. You can tell that there has been a mass normalization in this problem because we get unit values for generalized mass. Here are below the resulting eigenvectors that are given as a part of the problem. Notice that they are not normalized with the unit maximum value, but rather have been normalized by that mass normalization as I mentioned. You get some feeling for the physical numbers here as these are entered. And for those of you who know the theory, you understand that these terms on the generalized stiffness are related to frequency squared. But you have to have the proper units to make that make sense. We're carrying all four vector components. They're in column form. And those are the only four eigenvectors for our flexure problem in the xz plane. So this again ought to be an exact answer if we carry all four modes. If we decide to truncate and only carry out a 2-mode solution, and that actually was stated, then we have an approximate solution. And in that case, we just mean that we're taking these first 2 modes and throwing away the information in these higher 2 modes. Now we need to solve the uncoupled modal equations. They're shown here. There's no damping in the system. Our generalized force is this inner product. We put in the proper numbers here, so we have our column vectors transposed times this force vector on the right, and you get a reduced force vector here then, or a generalized force on the system. And we see that the second mode has a larger amount of work that can be done on mode 2 than the force can do on mode 1. And that has to do with the reverse nature of the load, that it just naturally fits the shape of the second mode a little better than the first. Now that doesn't mean that this second mode is going to dominate the response, because it takes more energy for it to move, more kinetic energy, so we will see how the battle proceeds here. Let's now write out the differential equations of motion. Here's our newly found force on the right, and it's at roughly 30 hertz. The system is on the left here. We're going to assume that it responds in a steady state way also at the roughly 30 hertz level. So we'll assume 180 radians per second on a set of modal participation coefficients here. When we uncouple the equations and solve for the first participation coefficient C1, we're able to solve for that and find this value. It comes out negative. If you think about it for a second, that makes sense. We're driving this system at roughly 30 hertz. That's above the first frequency, which is near 10, and below the second one that's near 50. So we're driving this system above its first natural frequency. And you can see we have this out-of-phase behavior. One might be tempted at this point to think that the tip load is doing less work and that somehow the midpoint node is driving the system in this case. And that would be true if this was a quasi-static problem or below the first resonant frequency, but we're above. And remember, in a single degree of freedom system, you get that 180-degree phase reversal. So this is not unexpected. This is a reasonable result for the contribution of the first mode to this dynamic motion. Now let's solve for the participation of the second mode. We do the same thing as we did before, uncouple the second equation of motion and solve for C2. And when we do, we get this number. Now that number is a little bit smaller than the earlier one, and so we see that the second mode will not participate quite as much. Notice this time the force field is in phase at the tip with this particular mode. Well, we're exciting the system at less than the natural frequency of the second mode, so we're below resonance for that particular mode. So it kind of makes sense that you're in phase at the tip where more work is being done. Now, if we'd like to add up those two results, we do that by recovering in this mapping sense from the generalized coordinates back to the physical coordinates. And if we put in a specific point on the eigenvector such as the tip, then we can get the actual numerical values here. So here's the participation coefficient of the first mode times the tip displacement of the first mode. Coefficient for the second mode times the tip displacement. And in this case, the winner is the negative quantity contributed by the first mode. So at the tip, the fundamental mode, that is C1 and Phi1, is dominating the motion. Remember that this is a half amplitude, and when we put these bodies together, I didn't really plot out the full shape, but it appears to be going down at the tip, so it would go something like that. And then if I'm a good sketcher, this would have to come back down this way and go back up. So as always, we're looking at an envelope of the motion. For our second problem, let's look at damping and look for existence of synchronous modes. We'll look at both the Rayleigh and the Caughey forms of the condition for that to happen. I'm going to propose this mechanical system with 2 degrees of freedom with this inertia matrix, damping matrix, and stiffness matrix. The first question is whether the damping matrix is a type of Rayleigh proportional damping. And then secondly, does that damping matrix satisfy Caughey's condition? Showing whether a damping matrix is of a Rayleigh type is actually straightforward, because you just see if you can solve for the proportionality coefficients alpha and beta that make that approach work. And here's the general statement. I should put a question mark up here. Is it true that you can decompose this matrix into these 2 terms? Now, this is not arbitrary in a sense, because there are 2 unknowns and there are 3 coefficients here that have to be balanced. Because of symmetry of this matrix, there are only 3 independent terms. So this won't happen in all cases. The first thing that might have occurred to you is that, well, it always works out. No, it doesn't. Let's check it though. The first equation, the upper left coefficient gives 3/10 as alpha plus beta, and then the second term gives 7/10 equals 3 alpha plus 2 beta. Those are solved simultaneously and you do get a solution. So far so good. But now you have to check the third equation, the third independent equation here. 2.2 equals 10 alpha plus 6 beta. And when you do that, you find that that's identically satisfied. That's kind of a compatibility equation. So yes, the answer is that damping matrix up here is a Rayleigh type of damping, of proportional damping. The second question we're asking is whether a kind of proportional damping that satisfies the Rayleigh law is also a Caughey type of damping. Now, the Caughey formula is the necessary and sufficient condition, and in a sense it's the weaker of the conditions in terms of what it requires of the damping matrix. And with some thought you would realize that all Rayleigh damping must be also a Caughey type. In other words, if Rayleigh, then Caughey. And we can work that out theoretically first before we plug the numbers in. I'll make a little theorem here. Any Rayleigh damping matrix satisfies Caughey's condition, and then I prove it. This is kind of a fun thing. I've never seen this in any textbooks. You put in for the damping matrix at the front and at the back the Rayleigh proportional damping. And then you start matching terms and canceling them. You get both the mass and mass inverse term on the left here and on the right, which cancel, and then the stiffness term here that cancels. And so in fact you get that the Caughey equation is satisfied. So it is true, any Rayleigh damping matrix also satisfies Caughey's condition. But Rayleigh's is easier to work with, and that's why people still use it a lot when they want to discuss academic problems. Now let's work out the numbers for our specific example and see that Caughey's criterion is satisfied. To do this, you need the inverse of the mass matrix, which I do here, and then I directly form Caughey's condition here. You turn the crank, and I do it by first multiplying the second pair of matrices on this side, and I do over here a product of the first two, getting a little creative here, into this. Then you finally multiply those two on the left, those two on the right, and lo and behold, it does work out. So at least in this specific case, we show the reduction from the Rayleigh criterion indeed also satisfies Caughey's, and then we had a theorem that shows that that always